Are we good with this? Okay. Well, good morning. Thanks very much for inviting me. It's a great pleasure to be back. So I have about an hour to tell you about a bunch of different things, all sort of under a common umbrella of information-theoretic location management. Now, as the name itself will tell you a little bit, we're looking at sort of classical location management problems like, paging, location update, and so on. But with a slight twist, we are trying to see where results from information theory or coding theory can apply, and we can reuse them to make something sensible. So I should say up front that our goal as part of this work is not, I'm not an information theory person, so we are not really devising any new contributions to information theory. The contribution is more like using well-known results in information theory, but within the sort of the networking umbrella, which honestly my perception is that a lot of the networking community hasn't been doing that. It's been a more ad hoc effort in a lot of the networking community. So we believe that there should be more theoretical underpinnings to a lot of the networking research. Okay, for some reason all right, part of this work, I supervise a student and his advisor at the University of Texas at Arlington, so I just wanted to acknowledge their contributions. So I'll quickly go over some of the background work, and because given sort of the broad nature of the audience, some of you may not know some of the stuff. But I'm sure you know this. This is sort of wireless networks 101. There are really, when you talk of location management, when managing the location or tracking mobile users in a cellular network, you have two fundamental operations. One is the location update or registration, which essentially the mobile, if the onus is on the mobile node to say that, I'm here, I'm at this cell tower, I'm at this cell, I'm in this registration area, so on. And when the mobile does this, what it happens is it reduces the uncertainty as far as the system is concerned, because the mobile is sort of checkpointing its location at different points. Now, in general, again, if you look at the broad picture, the location could be expressed in two different ways. It could be relative to the topology, which is like the cell tower I'm attached to, or it could be absolute geometric coordinates. But if your idea is to track the mobile only to sort of communicate with the mobile, then it's the symbolic coordinates is more natural, because you only need to know the relative to the topology where the mobile is. And the converse of this is the paging of the system search. So since the mobile cannot update on every movement because all the signaling overhead, there is some sort of ambiguity about where the mobile currently is. So when a call comes in or traffic comes in for a mobile node, the system has to search to find out where it is. So again, there's been a lot of work in this area in the past sort of 10 years. Again, a lot of work related to what are the optimal paging algorithms, with different paging strategies, location update strategies, like reporting centers, distance-based, movement-based, paging profiles, and how to construct paging profiles, and so on. So when I talk about how to look at it from an information theoretic perspective, some of the key things to realize are that fundamentally, this paging problem or the location problem is really about resolving the uncertainty of a mobile's location. So uncertainty has a natural role in information theory, which is like any random process. You want to predict the state that a particular random process is in at a particular time, and that's what the mobile's movement sequence, you can think of it. It's a random process. So we can use information theory to at least abstract some of the concepts out. And we need a framework to do this mathematically, and that's sort of, I think, my personal belief that there hasn't been too much of work in developing a theoretical framework for studying mobility patterns in this area. And you'll see, you can use all these concepts, and the two that I will particularly talk about today is entropy and rate distortion, and some modifications on that. So again, quick background on what's the current, this is not state of the art, but this is what cellular systems employ, and you know that what you do is you have all these blue cells and you club them together and you create these big registration areas, because you're essentially reducing the signaling burden on the mobile. So what the mobile does is every time it enters a new registration area, it informs the network that this is my current registration area. So this is the first update, but then the mobile is moving, and as long as it moves in this registration area, it doesn't send any more updates. Moves to a new one, sends an update, and then keeps moving in there. Again, it moves to a new one and sends an update. Now, after that, it moves. But now when a call comes in, that particular system doesn't know where the mobile is. So in the current system, you just page all the cells in that registration area. But there's a lot of work and ways to do this better and so on. So some points that I want to mention, again, just to give you a little background, I mean, my motivation in doing this work is not sort of purely academic, because, you know, part of like the industry background that I have is, you know, we have to say that this is actually practicable, it can be implemented with current infrastructure and it's relevant and so on. So this scheme is global. So one of the objections with the current scheme is that it doesn't exploit the individual statistics or patterns of each mobile node. So because different mobiles have very different characteristics and you want to exploit that information. I'm not sure why it's getting cut off at that edge, but one of the most common observations is that you can do better than paging all these cells. And sort of there is this fundamental result, you know, that was, I think, first published by Charlie Rose, that the optimal, in the case of, you know, without any latency constraints, the best way to page a set of cells is to start with the cell where the mobile has the highest probability of residence, then go to the second highest one and so on. This is kind of an intuitive result. And you can do that. So what is like the prior research, most of the prior research? So the global scheme does not consider mobile or application specific characteristics, and some of those will become more relevant because in the second half of the talk I will be talking about sort of a multi-system integrated cellular network and the challenges associated with it. And one of the things that we are seeing is that mobile nodes are becoming more diverse, because as a common access infrastructure really becomes true, it's not just cell phones, it's pagers, it's laptops, all of which you know have very different battery capabilities, so they can tolerate very different application profiles. So the paging latencies associated with them are different. You know, the constraints on paging, their tolerance for higher update rates is different, because with the laptop you don't really care even if you update on every cell. There are lots of MN specific update schemes proposed in literature. There's like one big drawback of many of these schemes, which is that they all depend on certain assumptions about the mobile's movement pattern. So they believe the mobile, you know, like there's dead reckoning schemes, for example, which believe that the mobile, once it picks a particular movement direction, it kind of stays in that sort of cone of movement for a while. Then there are schemes that construct mobility profiles, you know, believing you repeat the same pattern every day, because, you know, you have sort of like a you know, you go from home to work and then you come back via a certain route and so on. The model construction is typically offline, or it's very expensive, and that's one of the problems with a lot of these suggested solutions, that first you have to learn the mobile's movement model, you have to customize it, and that takes time. And there's better paging schemes, which I already talked about. So let me jump into sort of the fundamental, again, theoretical bounds on this. So the question we're asking is, what is the minimal amount of signaling that any feasible location scheme would generate to track this mobile? And the answer is tied to the randomness of the mobile's movement pattern. The more random the mobile's movement pattern is, to track it, you have to spend more resources. The more predictable it is, you need less resources. And this is the classic idea of information theory. So you look at the movement of the MN as the sample path of a random process, and how much information is inherently contained in this random process. So, you know, you have the basic entropy formulation, and the key idea is that the more random a source, the larger is its entropy. In other words, that each event generated by that source carries much more information because you have less predictability about it. If it was very predictable, then you already knew it. You don't need to actually sample and get this information. I'm going to skip, you know, I'm trying to go, this is partially a mathematical talk, but I'll try to keep it to a minimal. This is stuff, you know, I mean, those of you who have taken information theory will know this. So this is the definition of entropy for a random variable. For our interest, we probably need the entropy of a random sequence. There are two ways to define it, conditional and joint, and they converge in the asymptote, so on. For a random sequence, the entropy of that random sequence defines a lower bound on the number of information bits needed per symbol. So for each symbol generated, you need this number of information units to actually capture what that sequence was. So with infinite memory and no restrictions, this bound can be realized. So this you know, Shannon's proof is like, you know, it's constructive, but you need infinite latency and so on. So again, the intuition, as those of you know, is like, you know, only the typical sequences will manifest themselves over time, and that's only 2 to the power hx, so you need only hx bits per symbol. So one of the observations is, if you look at this as a random process, then and if you measure the cost of any signaling scheme, you cannot hope to use fewer bits per symbol than this entropy. So having said that, there is a caveat, and I'll come to that caveat in a little bit. You cannot use lower bits than entropy if you really want to capture the movement of the mobile accurately. And that's one of the things I'll talk about in the talk, that in many situations we can do better, or for different trade-offs, we don't care about an accurate reconstruction of the mobile's movement. In that case, we use rate distortion theory and say, we'll tolerate distortion, but how can we lower the rate? So some of this work, this is actually a slightly older work, the lazy update scheme. Now, this is not the theme of the talk, but just to give you a background, I think it's essential to spend at least 10 minutes to explain this scheme, because the rest of it is sort of natural analogs of this scheme. So what the lazy update scheme is, you have the mobile's movement sequence. So what the mobile does is that it has to convey this information to the system. So what it does is it looks at this sequence as a symbol of strings and does an entropy coding on this. However, to do an entropy coding, you need a code book. Now, unfortunately, the best code book depends on the mobile's movement history. And you don't know the history until it is history, because then you have to observe the mobiles over the last 2 years and then construct the code book. So we really need an online learning algorithm, an online code book generation algorithm. And there is actually this classic Lempel-Ziv text family of compression algorithms which are online and which still give you the asymptotic entropy bound. So again, I'll give you an example of what this online scheme is. So you can think of this as the mobile's movement sequence. So these are different cells. If you think of this is how the mobile is moving. So what you do is you first break it up into, and this is at the mobile end, you break it up into non-prefix segments. So you start with A, J, L, then when you go to the next L, you've already seen L before. So you're making them up into batches such that in any batch, only the last symbol makes that symbol unique. The rest you've already seen before. It's a prefix of some other, already some other symbol. So then what you do is you code the new sequence as the ith entry in your code book. So this is what the mobile is doing. So you start off saying your first entry in your code book is A, your second entry is J, the third is L, the fourth is a combination of L and O, the fifth entry is O, the sixth entry is JH, because you have seen J before, it's the code book 2, but you haven't seen JH. And then what the mobile does, it only sends the index of the code book up to what it has constructed and this new symbol. So what is happening is to the system, it's sending this sort of root of the tree saying I haven't seen anything before, and this is the new symbol A. Then I have symbol J, symbol L, but then it's saying what I'm sending you now is the third entry in the code book, which the system already knows, and an extra O, and this is the fourth entry in the code book. Again, this is also a classical theory. Using this online algorithm, you can prove that the number of bits in the asymptotic case reaches hx, or the entropy of the sequence. Let's give you a quick outline of what the decoder, or in other words, what the system does with this information as this is coming in. So the one thing you realize is what we have done is that we don't send updates at every transition of the mobile, but we are essentially building up more richness in the updates we send. We are compressing the output from the mobile, but we are not losing any information. So at the system end, you can take that information and reconstruct the actual sequence of the mobile up to the point that the mobile has sent information. Once you reconstruct it, what you do is you actually build this trie structure. So what you do is for every A you get, you build an AA, you build it down the trie, and one of the modifications you need for this particular case from Lempel-Ziv is that you have to update the prefix of every suffix of the phrase. So for example, you get the phrase JAA, and you look at what are the different suffixes of JAA. You have JA, A, and A, and you look at all their prefixes, and you add one to each of them. Now again, I'm not going to get into the details of the math of this, but what do you do with building the trie? The outcome is, again, remember that result I said, which is that you want to page in the decreasing order of probabilities. So you have to construct the probabilities in some way. But that trie basically gives you a way to construct these probabilities in an efficient way. The observation is, suppose the mobile has reported A, J, L, and it has not reported anything after that. One thing you can know is that any new pattern, the mobile may have moved after the last report because it's not sending anything at every sequence. But anything that it has moved, it has encountered in the last report, you have already seen before. It's already somewhere in your trie. So all you need to do is you sort of weigh the probabilities of how these different patterns are in your trie. And the way you do that is it's based on prediction by partial match. Now this is sort of well-known stuff. I don't want to get into from a statistical context, but I don't want to, again, I do want to skip the math, but I just want to highlight the following things. So suppose you come to this point and you think, what are the possibilities? So one possibility is that the next sequence that the mobile hasn't seen is like, say, JL. So you look at it and say, what are the different places where JL could occur? It could occur as a completely new JL, or in this case it doesn't, but suppose there was an L here, this could be AJL that the mobile has reported. Then because you look at the last update, and let's say the last update was, again, let me go back. The last update was JLL. So anything that you see after this is going to be, you look at the probability of JLLA, you look at the probabilities of LLA, you look at the probability of LA, and you look at the probability of A, and you weigh them by how many times you've seen them before. And having done that, you finally get the combined, you get the unconditional probability of each sequence, and from that, based on what the last entry in that sequence is, you can get the unconditional probability of each cell. Now again, this is all known. So this is all sort of the background of this work. Now you know this stuff. So some of the observations on the basic lazy update algorithm is that the entropy coding ensures that this update cost approaches entropy asymptotically. However, this is a purely MN specific scheme in that every mobile constructs its own history. We don't use the registration area infrastructure that we currently have. And it cannot accommodate preferences such as battery constraint, paging constraints. What I mean by that is, if two mobiles, do the thought experiment, two mobiles have the same movement pattern, but one is a laptop and one is a puny pager, they will both send exactly the same update. So the update cost on the mobile end will be the same. And we have no way to do a trade-off. So the first part of the talk is, we want to develop a framework for trading off. As I give you the trade-off, there's one thing to bear in mind. That this lazy update scheme that I described is optimal in the total cost. We can never better that. What I'm talking of is a trade-off where I will incur a higher paging cost.
Is the lazy scheme implemented anywhere?
In any practical, no, not yet. Not that I know of.
Are there plans to do that? Or?
Not that I know of. Within IBM we made noises with some cellular providers, but it's too far out, I think, honestly. But what we're doing is a trade-off, because we are saying that we don't care about the total cost. We want lower update cost, and we're willing to pay higher paging cost because the network resources, okay, so we spend some more cycles, some more energy. That's fine. So the first thing is we want to develop a framework for doing this, so that different MNs who have different update restrictions or different paging delay tolerances can do different sort of updates. So the fundamental idea of rate distortion theory, which I already talked about, is if you want an update cost lower than HX, which is the bound of lazy update, then you have to accept information loss. There's nothing you can do about it. Okay, definition of rate distortion, you have to define a distortion measure, and then you get two sequences and say what's the distance between them, and it's the infimum of that, but okay, let's skip over that. So the idea I'm giving is very simple. You will do distortion through registration areas. So we have this same registration area structure as before, but so what we do is we do quantization. We don't look at the mobile's movement on a cell-by-cell basis. We just try to capture the mobile's movement on a registration area by registration area basis. Unlike PCS, however, unlike the current system, every time you move from this registration area to this one, you will not generate an update. Because what we are looking is, we are now going to look at the array layer movement sequence. So let me explain that. So there are two sequences, one I call lazy array and the other array lazy. They both have, the paging schemes will be identical, because once the trie is constructed, they will do the same thing. But let me give you the two schemes. What's lazy array? I'll give you, it's best explained with the example. So this is again the original sequence on a cell layer. What the mobile does is it first quantizes it into the registration area. The big, the capital symbols denote the registration area. So it gets this new symbol because all ABC map to AAA and so on. And now, this is the sequence on which it does the lazy update. So it encodes A, AA, P, PP, and so on. And then everything else is identical. Then it's going to say, it's going to send A as the first entry in the code book, 1A, this is the second entry is the first entry followed by an A and so on. Now this is the lazy array algorithm. Seems kind of obvious, right? So what's a property of this? So the property is that if this random sequence you treat as a random sequence Y, again it just follows from the Lempel-Ziff properties that number of bits required will approach HY, the entropy of this random sequence. So what are some obvious results? First of all, HY is less than HX. Anytime you do quantization, and the reason for that is HY given X is determined, given a particular organization of cells, this mapping is deterministic. You know, given a cell, what array it is in. The reverse isn't. So HX will be larger than HY, and that's the property we're exploiting. Now, here's another property, and this, I'm going to do a little bit of hand waving. I'm not claiming that we'll achieve the rate distortion bound, because that needs sort of vector quantization over infinite sequences. However, in any practical scheme, if you just cascade a scalar quantizer with a lossless entropy coder, which is what we are doing scalar quantization by quantizing the cells into arrays, then we're doing entropy coding. We do get very close to the rate distortion bound. Now, is very close good enough? I'm not making that claim. However, for like memory-less sources, you can get to about 0.255 bits and symbol of the entropy bound and so on. So we're not going to be doing terribly worse than what we can do optimally, but with a practical scheme. That's the point I'm trying to make. So asymptotically, is this? Okay. So one of the things is what's the distortion measure? And I have to say that I don't really have a formal definition of a distortion measure because it depends on the paging scheme. I cannot really define, what the difference between two things is. But one thing should be clear, that the larger the size of the array, the larger the distortion, because there's more uncertainty in the mapping you're doing from one cell to an array. So what I'm proposing, therefore, okay, so let me stop. So the claim I'm making is the following. I don't know exactly what the distortion value is, but given that there is a distortion value, this scheme will get you very close to the rate bound on that distortion measure. With this, and again, so I can think of fancier algorithms to do this, but we are walking that fine line between, something theoretically very interesting, something very practical. Because all we did is we took the cellular PCS infrastructure and we did entropy coding instead of updating on each particular sequence. Now there's a slight variation on this. You go back to the same sequence and you quantize. Identical two steps. Now then what we do is we compress this even further. We eliminate the self transitions because there's a lot of because you're going to move from one cell to another in the same array many times, you remove that. Once you eliminate the self transitions, then you encode the remaining stuff. You send this out. So some of the obvious things you would expect is because you're eliminating self transitions, you're losing higher order context information. So the entropy bound of this sequence will actually be larger than the entropy bound of the previous quantized sequence, because there's less predictability here, because you are definitely jumping to a new sequence. Okay, so that's now what's the paging algorithm? I told you they're identical for both. So like the original lazy update, what you do is you compute the relative probability, because now your symbols are arrays, registration areas. You compute the residence probability of different registration areas, and here is where we make a leap of faith. Because we have lost the information about which cells you visited, we make the assumption that this probability is uniformly allocated across all cells of this registration area. So as far as these cells are concerned, you can page them in any order, because you don't know, you just don't have any information about which one is better than the other. So we normalize it by the size of these. Yes.
Your assumption is kind of weak, because sometimes we can know which cell it might be if it's from the other registration area. That the next possible cell just could be the boundary cell, not the center cell. So in that situation, if you know your previous symbol, your previous registration area, then that is not the uniformity distribution.
Yes. There are 2 points to this. First of all, you typically, if you know your cellular topology, you will know exactly which, if you move from which cell, you'll know the likelihood of which cell you move to, or a set of cells. But if you're only getting information about registration areas, then that information becomes even coarser, because you could move from 3 cells in this registration area to now 9 cells in this registration area. So I agree with you that you can do better if you have topology information and you utilize it more intelligently. So the idea of this scheme, and I'll get to this more explicitly in the multi-system case, is we don't want operators to be exposing or utilizing their topology information. So we want to construct a scheme which is sort of more algorithmic and generic. But your point is well taken.
This is at the provider side, right?
Yes.
So what prevents the provider to keep track, for example, of the original data that you provided, these little a, little b, and then keep track of, for example, of kind of a mobility pattern in a coarse way as to how a particular mobile moves, then you could, in a sense, make a correction to this formula.
Yes. Well, the point is that this sequence, this is only seen by the mobile node. The system never knows this. The system is only getting this compressed, you know. So, okay, now the usual, I'll give you some simulation study. So it's done over a period of 12 weeks with 250 cells. Again, not much to say about this, but sort of 3 different, we had 3 different states, and the mobile is moving again from home to work, but with enough randomness in it. But so just let me give you a couple of graphs, because the results kind of are expected. So this is the updates, number of updates you see per day. So with the array-based scheme, this is what you see, approximately on the order of about 50 updates per day. This line here is the lazy update, the original. This is the entropy bound. Now, with lazy array, which is where you include self transitions, you have to send more updates, so you get this. So you're lower than this, and with array lazy, you get even lower. But this is only half the story, because you have to look at the total cost, you look at the paging cost. And the paging cost, not surprisingly, again, the array-based scheme has more paging costs. I mean, we can't claim anything by saying we are better than this scheme, because so many schemes are better than this. But you look at the lazy update scheme, it has the lowest cost, because that's getting the richest information about the mobile's movement. But if we get coarser information, then we are doing in percentage times twice as much. Now this might seem like a lot, but the whole point is that this was precisely our objective, that we wanted to reduce the mobile's burden by any arbitrary amount you wanted to, and have the framework increase the paging burden on the system. So one way to look at this graph is if you combine the paging and registration costs and weigh them. So you do a trade-off and the number of cells in each array. So as you increase the number of cells, the paging cost goes down, the update costs go up. And if you, depending on how you weigh them, you can get a total cost below what lazy update gives you. But all I'm saying is for different categories of cells, mobile devices, you can pick different array sizes, and then you basically have the space to play off in. All right. I think I'm doing good on time. So is there like a quick, I can take a quick question if people have problems up to here, or I can continue. All right, so I'll continue. So I'm now switching to a different problem, but this is sort of the more the problem for the future, which is location management and integrated multi-system network. Okay. So what's a multi-system network? And this, this was first used as a buzzword with 3G networks. Now that 3G is not taking off, it's being used as a buzzword with 4G networks. Who knows? I mean, maybe this will be the 5G network of the future. So the idea is that you have different individual cellular networks. Everything I told you was for one cellular network. Now I'm saying there are different cellular networks. There's a satellite, there's a cellular packet-based, wide area network. There are wireless LAN hotspots. We already see this. And these are managed by different providers. So these are completely independent operators. And their cells have completely arbitrary overlap because they don't know about one another. They don't plan for one another. They could overlap. They have very different cell sizes and so on. And each system will have its own sort of location and update policy. One observation to make, an interesting observation here, is mobile devices now have multiple radio interfaces. So it's no longer a cell phone. You already have some cell phones. I think the Ericsson phone now has wireless LAN. Both Nokia and Ericsson have Bluetooth on it, which is slightly less interesting in some sense because it's more local area. And one of the more interesting sort of predictions one can make is that it's likely that you'll be using multiple interfaces simultaneously for different types of communication. So in fact, at IBM, we have prototypes and, sort of, it's not research, more sort of demos that show you can take your phone and, have your internet browsing, even if you have like a multimodal communication. So, you're talking to someone and viewing charts, and they come over different access technologies, and you synchronize them. So you are using different providers. Now this is actually a very interesting phenomenon, that different interfaces are active at the same time. So here's the obligatory cloud. So we've seen this picture in the past. One distinction from sort of the hierarchical nature of networks in the past, I mean, a lot of work done in this area, then it was assumed that the hierarchy was controlled by one provider. So you had picocells, microcells, macrocells, and there was a lot of work on how you can switch calls for fast-moving users to the macrocell and slow-moving users to the picocell to minimize the resources and blocking and so on. But here, these are completely different providers, and also the assumption is that one radio, one mobile device can have multiple conversations open on multiple technologies at the same time. Let's get to the challenges. So in this particular environment, the mobile has a set of challenges. The first is when to update. Now, cell transitions in different, so each technology, I'll use the term subnetwork, because now the network is a collection of cellular subnetworks. So each cell transitions occur at very different frequencies, because some are very giant cells, like a satellite cell. You don't really transition that all too often. But if you have disconnected wireless LAN hotspots, you're making transitions much faster. Where to update? You have multiple providers, so do you send them to all providers? Do you send them to a centralized place? So on. How to page a mobile? Now, I'm making the assumption that, in fact, that's an interesting open problem that I won't address here, and I don't have an answer for, is that suppose a call comes in. So there's work that says which is the best subsystem or subnetwork to use to deliver this call. That could be based on policies, like, this is a voice call, so use a cellular network and so on. I don't address that, that's an open problem. But I'm making the assumption that you know which cell, which network you want to page. Somebody has made that decision that this call needs to be routed over this subnetwork. Then how do we page it? And this, again, as I said, one of the challenges in doing this research is to walk that fine line between doing something too dumb and doing something too impractical. So one of the constraints that we put on the system, and this is something that I have practically experienced, you want all these different providers to work together, but they're very sensitive about exposing their topology information to each other. So you cannot mandate anything that's, we know the overall topology database, we know which cell in this subsystem maps to is a neighbor of cells in another subsystem and so on. The way we look at this is that we take that entropy notion, and this is an obvious generalization. So with n subsystems, we now look at the mobile's movement symbol as a collection of subsystems. So it's a vector valued random variable now. So what x1 will indicate is in subsystem 1 what the cell is, which cell it's in. x2 will indicate in subsystem 2 which cell it's in, and so on. Now we model the mobile's location probability as a joint distribution across all these subsystems. So the probability that it is, okay, let me explain this notation. The probability that it is in the x1 cell of subsystem 1, it's in the x2 cell of subsystem 2 simultaneously, because these are all overlapping. And then you define an entropy on this joint distribution. One thing to keep in mind, although they're overlapping, because these are different technologies, you have to allow for the fact that you will be disconnected from some subsystems quite often, possibly. So this x2, we have this additional variable, like a unique cell called phi, which is the disconnected cell. So if you're in that cell, you have no connectivity. Then to get sort of a bound on the location cost, we go to a weighted version of the entropy. Now, weighted entropy, when we did a search, the terms were taken to mean a lot of sort of different from what we had in mind. There, the notion was, related more to arithmetic coding and, what weights to assign to, like, as you go from real to integer space, what weights to assign and so on. But one of the things, again, in this general framework, this doesn't seem to work most of the time. Can you make out that red dot? Okay, I guess. So One thing we assume is different subsystems have different location update cost and paging cost. It's not uniform. That's another big distinction. So having said that, then we define the weighted entropy as again the limit of the conditional entropy, where you weigh which cell you're transitioning by the LUI. Because if you are moving, if your update is in subsystem, say N, then you should weigh it by the location update cost in that subsystem, because that update is in the domain of that subsystem. So this is what I mean by weighted entropy. It's not a very fancy term, but it gives you the message. So that's one of the unique definitions. Now, as far as the paging is concerned, we have some interesting advantages, challenges, constraints. The first thing is we can do better with paging if we also throw the call state in. This is much better. So another observation we make in when paging was first designed, the assumption was you are paging an idle node. Otherwise, why would you page? However, with multiple interfaces, we have this interesting problem that there is nothing known as an idle mobile. The mobile could be idle in one subsystem, active in another. So you're having a voice conversation going on, but your wireless LAN radio is gone to sleep because you have no data packets coming over it. So in that sense, knowing that an MN is active in a particular subsystem, you can actually improve paging through redirected paging. So let me show you the example. So the example is that in subsystem SJ, the mobile is active. It's idle in subsystem SI, which needs to place a call, which needs to reach the mobile. So the conventional way to do this is for mobile SI to page in its cells. And if the mobile happens to be in any one of the cells of that subsystem, of the subnetwork, it will respond. Here's what we can do better. This subsystem can ask this subsystem, can you please tell the mobile that, I want him to respond back? So you're relaying the paging request this way, but this is a unicast message. You don't have to broadcast, you don't have to search because the mobile is registered. So if you had this knowledge, you would do better this way. When I say do better, remember there's a sort of an interesting trade-off, because this is a unicast message of PGJ, where that would be like depending on the number of messages you broadcast times PGI. So it's not always true. I mean, depending on the weights you assign that a unicast is better than a broadcast. So it depends on the subsystems and so on. So how do we combine the location information, the session state information? Now, in general, if you believe that you had a central architecture which was on the call signaling plane, you would know exactly when calls were active, when sessions were active for each mobile node. We don't make that assumption, because if you look at the architecture, the location management subsystem is actually divorced from the call management plane. So we don't want to break that. So we don't make the assumption that we know for sure when a call is on and when a call isn't on. And we are just going to predict it by having the mobile give us some statistical information. So the way we do that is we also think of another random variable, which is a binary n-valued, where Z1 is 0 if the mobile is idle in S1, it's 1 otherwise. So having done that, you can create a 2n-valued vector sequence. And I'm giving an example for 3 subsystems. So the mobile is now in the 5th cell of subsystem 1, it's disconnected from subsystem 2, and in the 4th cell of subsystem 3. It's active in this, and it's, obviously if it's disconnected, it's idle, but it's also idle here. And this is the state. This is the composite state. And one of the things is you can make simultaneous transitions from, you could go from phi 0 C430 to say some cell here 0, and you can also change the cell here. But we can view this as a successive transition, so we don't lose any generality by treating it as a one-off transition. So having done that, what's the update procedure? So we're going to update that. So that random variable is what constitutes a random sequence. So that's on which we go back to our lazy update scheme. So we are going to look at the sequence, the mobile's combined mobility and call state vector as a sequence. And that's going to be Y1, Y2, Y3. And I represent them symbolically as these things. And you then break it up into non-prefix segments. You know the drill by now. This is what the mobile updates to the system. How do we use it? So I've given you the mobile side. How would we use this system? So the one thing we can do is we can construct the decoder trie. Now the elements are vector valued symbols. Now each vector value, there is a different symbol for, so rho ij0 is the probability that the mobile is in the jth cell of subsystem I and it's idle. Rho ij1 is the probability that it's active. So you can get these unconditional probabilities and combine them for the fact that the mobile is in that subsystem, in that cell, in that subsystem, in either state. That's kind of obvious. And you can get these are symbol level probabilities, and you combine them. So you get this overall probability. Then, again, sort of intuitive extensions of the basic result, you have to weigh the probability that the mobile is in that particular cell. You divide it, you normalize it by the paging cost over that subsystem, because different subsystems have different paging costs. So once you do the normalization, then we proved this. Then the optimal scheme is to go in the highest, pick the highest one, the highest normalized paging factor, try that cell, then pick the second one, try that, and so on until you succeed. So and this, just to address one of the points, sort of address. If the call is to be complete in subsystem SI, you may always argue that if you go this way, we have lost information about sort of the topology because if you're in a particular position where you know that it's a disconnected, there's no coverage in subsystem S2, then there is no point in even trying to construct these probabilities and page cells in that subsystem. But for this multi-provider environment, we're making this assumption that there is no intersystem topology and cell structure information available. So without this information, this is the best I can do. Now, so that's the overall theoretical framework in the upper bound. Now, I'll give you 3 different ways we can realize this, and they have sort of pluses and minuses. So the most simple conceptual scheme is to have a centralized location register. So all these subsystems, they have agreed that they will send all their updates to one common node. And for those of you familiar with mobile IP, this common node doesn't have to be, the load on this is going to be humongous. So you can partition the responsibility of different mobiles to different centralized registers, just like you have different home agents for different mobile nodes. So, but what you still need to agree on, let's say that's the home agent, then every subsystem that you send an update to, they will relay it to the home agent, every such update. And then that try, because there is one node which is playing God, it knows all that information, it can construct the try. And then when it comes to sending the paging messages, it will tell each individual subsystem that, if it wants to page Cij, it will tell subsystem I, please try this mobile in cell J and tell me if you succeed or not. And that's how the system will occur. And here's the example that as you move to different updates, they all go to the same CLR, and when you want to page, it will say precisely which cell you want to try. Okay, end of animation. So architecture number 2. So the first one has an obvious problem. There's a bottleneck. There are multiple subsystems, and will they all agree to send it to a common place, so on. So let's take the other extreme approach. The other extreme approach, the mobile basically updates to every subsystem, this entire sequence. So each subsystem then maintains a copy of this tree, this try. And so these tries, it's a single try, but it's maintained in multiple places. So it's a concurrent, copy of the same try. And then each subsystem can then play God and make the decisions, asking different systems to relay cell, page the movement, so on. Each subsystem, again, doesn't need the topology or call control information because the try is providing all the information needed. The disadvantage of this is obvious because now the update cost is not just, the weighted entropy, but for every change in the symbol update rate, you have to update to all the subsystems known. There's actually another interesting cost that we found out when we started implementing this, is you're disconnected from many subsystems for a long time. However, to keep the tries consistent, when you come back to that subsystem, when you attach, you have to send it all the updates that you haven't sent since the last time you were connected. So you have to store all this in memory. And that can be actually a serious problem, especially for wireless LANs which are disconnected, and which you visit like every, say, 5 days or every 10 days. If you have to store, so the memory requirements in the mobile node actually go up quite a bit. So it's interesting to study the features of this, but it doesn't look like it's going to be very practical. One slight twist, again, is, we made the assumption that you could page different subsystems, the cells in different subsystems one by one. Now, in all likelihood, to throttle the signaling load, each subsystem is going to say, you can't do that, you can't tell me which cell to page and so on. You can give me one message to say, page all idle cells. You can give me one message to say, page all active cells where the mobile could be in an active state, but you bunch them together. So if you do that, you have two types of paging requests. One is active paging, where you request the MN to register with the target subsystem only if it is active in that requested cell. And the other one is idle paging. So you say search for the mobile. So if you don't get this, the conceptual difference is, you go to subsystem S2 and say, page the mobile. Tell the mobile to register with S1. But with the active paging, you say, tell the mobile only if you know exactly where the mobile is. So don't waste any additional resources trying to find the mobile. That's active paging. With idle paging, you say, do your best. Try to find out the mobile by first paging yourself if you need to, and then tell the mobile to register in S1. Okay, I'm not sure. I'll skip this animation. Okay. It's simple math, but once you put up a lot of symbols, it's hard to, it's easy to lose an audience like this. So the active paging cost is easy to understand because you're doing a paging across the probability of residence that is active in any cell of that subsystem, and you normalize it by the paging cost because you're only going to send one message out. Because if the mobile is active in that subsystem, you know exactly where it is and you will unicast a message. The idle paging cost is actually slightly trickier because you still add up the idle residence probabilities, but now you have to condition it on the number of paging messages that you expected number of pages that you take in that subsystem. Because again, you're going to go the highest conditional first, second highest, so on. And therefore, one term in this, the numerator, is actually the conditioning term in the denominator of this. And that's how you eventually arrive at this. I mean, this is all in the paper, so this is more details. So now I give you what we think is a practical scheme, because both the first two are extreme. So it's centralized, but only with partial information. So each subsystem operates quasi-independently. So the MN generates updates in each subsystem purely. So we are going back to the independent operation of each subsystem. So the MN, only when it changes cells in that subsystem, it generates an update for that subsystem. So then the update cost in each subsystem is purely the entropy, based on the marginal probabilities in that subsystem times LUI. However, what each subsystem does, based on the statistics that it gathers itself, will update the central register intermittently of changes to its expected cost. So that what it's doing is, it's telling the central register that if you want me to page this guy, this is what I think my estimate of the cost is going to be now. And what we do is we have threshold-based triggers so that if, since your last report, you change more than 20%, you send another update, and so on. This is what each subsystem is doing. So the central register now only gets periodically, let me go back to this, periodically gets from each subsystem just a single value, which is the cost. It doesn't get every update, it doesn't maintain a try, nothing. It's much simpler. And then the algorithm for paging now is that, suppose subsystem SJ is trying to page the mobile. So based on its own statistics, it computes this expected cost. Then it goes to the central register and says, can you give me guys who have normalized paging probability higher than this cost? So in other words, can you tell me of other subsystems which, based on the current knowledge, you think will be better candidates for me to do indirect paging by? And you get back a set, and if that set is empty, you page yourself. If the set is not empty, you go one by one as the optimal mechanism. Now, clearly, because this is not an optimal, you're not using all the statistics, the cost will be higher than the algorithm 1. But that's always the case. There's an optimal algorithm that tells you the theoretical bound, but then you have to look at practical implementations. So again, just to conclude with a bunch of simulations, we have the same pattern, but now we have 3 different subsystems. We have the satellites, PCS, and wireless LANs, and these are arbitrary numbers on the relative location update cost. So for the satellite, we have the highest location update cost. For the paging, wireless LANs have the highest bandwidth. So we said, we don't care, the paging cost is lowest for wireless LANs. But for the update cost, from the mobile end, wireless LANs involve more transmission power. So the update cost for the wireless LAN is more than the update cost for the PCS. So, for some definition of real, these are some realistic numbers. Then we had a call pattern, which we had 3 distinct Markov modulated call states, which were weekday daytime, weekday evening, and weekends. Different rates, but the calls were generated according to some process, all that, some stuff here. So let's go to the update rates. So as far as the update rates are concerned, you can see this is the centralized update scheme. This is algorithm 1. Now this is what we would do with the current technology if you were all doing them all independently. Obviously, this was, well, one thing I want to say is not actually, at least as far as I know, not too many people have looked at this integrated cellular network problem. The only people who looked at it, actually people from Georgia Tech looked at it, but they looked at it only in the case of boundary registers. So only when you move from one cell to the other, not from one system to the other, not when you're simultaneously in both systems most of the time. So there is really no like prior work to do a fair comparison to. We just picked what you would do if you did like all of them independently. Now the decentralized scheme now obviously has higher cost because now you're sending the update to every subsystem for every change. Now the movement-based, the selective update heuristic, which is the third scheme, scheme 3, where you only send the deltas, that has a lower cost, and there are 2 reasons for this. One is you're only, because of thresholds, you're only sending updates only so often. But more importantly, with this scheme, we have lost the ability to take advantage of the call state information. Because remember I said now in each system, you're only sending updates when you're idle, and when you transition to a new cell. So since you have lost the call state information, your entropy is naturally going to be lower because you have one less random variable that you don't even consider. So the update cost is lower. But again, that's half the story. The paging cost, obviously scheme 3 will have higher because it doesn't use a rich enough statistic set and it's using higher costs. The centralized scheme does the best, and now this, you would say that the decentralized scheme 2 and scheme 1 should be identical. No, the reason is for this plot, scheme 2 uses that constraint scheme, which I told you that it would only send one message to each subsystem saying page all the cells in the subsystem together if they're active, if they're inactive, page this, tell the mobile to register only if it is active. It would send only those kind of messages. So the signaling load from a scalability, from a point of view of individual providers, they are more likely to like scheme 2 because you don't impose as much signaling overhead on them. But then you obviously do a little worse. But for us, we think that this appears to be a reasonably sweet spot. This or these 2, because you're obviously the paging cost is higher. We know how much higher than the best we can do, so we have provable numbers here. But it's much better than what we have done so far. And okay, I don't know why this getting cut. So this is the same graph as before. I just weighted the location update and paging costs together to show that if you look at the overall costs, this is the optimal, and you get about I forgot, it's about 30% higher with these decentralized schemes. So I think that's it. So just in conclusion, what I want to point out is I personally think there's a lot more work to do here, one of which as a problem, what we are working on right now is we believe that you can use, again, online clustering algorithms based on the pattern to basically define a collection of cells across different subsystems that should make one registration area. So we want to use the quantization concept in the multi-system case as well to have rate distortion trade-offs. But unlike the previous case where the cells were designed a priori, you just collected cells into a certain size. You want to do this, the optimal thing will be based on the individual mobile's movement pattern. And there are pattern matching algorithms, and so there's a body of literature again in information theory that we want to use. But the novelty is, I think, one of the messages that I do want to give out is sort of this integrated location management. The location management for a single system has been really studied to death in some sense. There's a lot of work on that. But for the integrated system, it's still an open, fertile area, which we haven't seen too much work on. That's it, if you have any questions.
Let's first let the speaker. Are there any questions? I think we have some time for questions. So here, if you as a customer, suppose I'm worried about my privacy, especially exposing my location to too many subsystems. How is it taken into consideration in designing a system like this?
Yeah, I'll answer the question, but before that I point out that the sort of the other obvious question, and let me ask it myself, is all this coding and stuff on the mobile node takes processing power and takes memory to maintain the trie. So the natural question, when we had with the paper is, okay, how big is this? And we found that for the statistics that we used, 15 kilobyte memory space is enough, which isn't terribly much, for cell phone. I mean, maybe for smart tags it's still a big deal, but for reasonably high-powered or medium-powered mobile devices, that's not too much. Now, the privacy question, so this system operates by each mobile giving out, so the subsystems don't know of one another, but the mobile is taking the initiative to send information about different movement, that I'm changing this cell ID in this system to the other one. We haven't considered the privacy problem as yet. I mean, this was purely a mobility. Not in this domain. I have worked in other areas. If you believe you have the centralized location register, which is a trusted source, then the privacy problem is easier to solve, because all your updates end up there, and you can use encryption to sort of conceal the information in an end-to-end fashion. And then the release of that information to different subsystems, you can control by policies, saying that, don't let subsystem 2 know of my whereabouts in subsystem 4, and so on. But if you go to a purely distributed scheme, the scheme 2, this is a problem. And I could give you a glib answer saying that the mobile could choose not to send the updates if that's the policy, but we haven't worked out the ramifications on how the algorithms, how much they would degrade by, or the specifics of that. But certainly an important issue to consider, not so much in cellular environments, but as you're talking more in personal spaces and offices and so on, that will become an issue. Yeah, sure.
The last thing that you said about the online clustering that you mentioned. I mean, in what way you imagine that you are going to do that, and how it's going to affect the system? I mean, this is going to be based on the mobility patterns of multiple users, and in that fashion you are going to group together the appropriate cells.
Yeah, that's exactly right. So I think the extreme is you can do different groupings for different mobile nodes. It's basically as you collect, again, it's an online algorithm, as you keep collecting statistics, the movement pattern, you can then make predictions that if we change the clustering this way, if we make these clusters, then we'll get lower costs, because these have higher correlation. These set of cells go together. But that extreme, I mean, really one of the things to realize is, and we are seeing this, the number of mobile devices is going up. Once you talk of an integrated infrastructure, I mean, it's not just a few 100 million cell phones. Now you have laptops, and a lot of us will be carrying active badges, with more ranges and so on. And in fact, one of the original ideas that you have one device for everything, that's still a good concept, but it's not really catching on. I mean, most people you see, they have a belt full of tools, like different devices plugged in here. So the answer, I think eventually the answer is going to be you'll have to have classes of users or classes of devices, and you do the aggregation on the aggregate statistics of that class. So
probably multiple clusterings of the same system.
Yes,
for the various groups.
For different groups.
Yeah.
But we haven't. I mean, again, we haven't worked that out, or that's not a published result or anything. But
I may have missed something. But
yes.
Within this clustering algorithm, who performs that?
Oh, that would be performed on the system side, and then that would have to be downloaded to the mobile. If you change your clusters, because the mobile is.
But then, going back to Richard's question, why would all these subsystems of these different providers cooperate?
Yes.
Because I mean, there is kind of a view of the world here that there is. I mean, everybody who has operated independently sees an advantage in doing what you are suggesting.
Right. Okay. So one point I want to, even in what I talked about, the first point to realize is that the systems don't need to cooperate among themselves. There is one guy who knows exactly the correlation between each cell in this subsystem and the other cell in that subsystem, and that's the mobile node. Because the mobile node always has the information, I was this ID and that cell that I saw together. So it's the job of the mobile node to send this information to whichever subsystem it chooses. So and the subsystems are therefore collecting this view of the world through the mobile node, not by cooperating with each other. So whatever information the mobile node gives it, that's the set of information that that subsystem can work on. So I think probably the question to ask therefore is, what is the incentive for the mobile node to be giving out this information? Now it's yes, probably.
Customers don't really care as long as the system can page you. The cost to the system is not necessary.
Yeah, so that's where I think that's why I say, this optimal reorganization. I mean, that is of interest to the mobile node, because you are lowering your location update cost. I mean, if you say that we're Nokia selling the smart cell phone, which lasts 3 hours longer than the other one because, we intelligently reduce your updates and so on, customers will buy that. I mean, there's an incentive for the customer, and the customer is not proactively doing this. I mean, in some sense, it's the handset manufacturer who has put the algorithm in there. You don't really control that. But does that sort of answer your question? Yeah.
How coarser will do when we send the registration area information rather than cells? Or how many cells are in a registration area?
Right. Okay.
In terms of the geometry.
Right. Again, the how answer, I mean, eventually it will be for the specific topology, but
The typical number in the current systems.
okay, I don't have a number for like a real current system. I don't, but these are the numbers which were based on data collected from some network that Nortel had deployed. I mean, I don't know which network it was. This was, this is from the University of Texas people. So what we find is that the paging traffic, from the optimal, the paging traffic goes up twofold. It's twice. But from the current cellular infrastructure, and that's kind of expected, it's 1/4 of that. So the optimal bound in some sense is 1/8 of what we have today from the paging. For the update traffic, we are actually saving about 60% from lazy update, and it's 10% of what currently the update traffic is. Now, you have to take this with a pinch of salt because we had a relatively regular mobile movement pattern. I mean, you have to account for the fact that people suddenly randomly move and change profiles. But so I think but you would still get substantial savings if you went to these intelligent schemes.
In the array range scheme, instead of truncating cell to cell transfer, it is A, and then you're sending only A. Instead of sending that, can we send the run level information like A should be called as A3 and send it for how many times the connection was in the same cell? Will that improve any?
Yeah, that's you're essentially sending the same information. I have to think about that as the previous scheme, with the difference that if you send 3 A's or 4 A's, you don't exploit the fact. See, again, you're not exploiting higher order statistics. That suppose each time you get only 3 A's, then it's not efficient to send, this time I saw A with run length 3, again I saw A with run length 3, A with run length, there's redundancy there. So the trick, surely you will do better, of course. The trick is to even have compression in the run length statistics that you send, which is, I've already told you that, the last 50 times you were seeing run lengths of 3 A's, and I'm telling you the same thing again without sending that info.
I thought that you were only sending an update message when you left a registration area. Because that was exactly the question that I mentioned.
Yes, no, I guess if you go back to this, only when you leave when you move into a new registration area, then you evaluate if the sequence is new. So even the
So it's not the case that you send only the A and then the P and then the Z and then the E?
no, in this scheme you only, I mean there were two schemes, one you send each new substring. So A, then AA, then P. And in this scheme, I guess, this is the one that you were...
No, but going back to the very first, don't worry, I mean the very first line that you had, you only send an update when you are changing registration area.
In current systems, yes.
Yeah, so it seems that, isn't it the case that then you would, if I look at the sequence that you have on the second line, that it would be first A and then P, and then Z and then E, so they would all be different from, I mean, you would never get two symbols that are the same.
Okay.
Consecutive symbols that are the same.
Yes. So what the current system is doing, if you will, see, this is the real movement of the mobile. And this is if you quantize it at each movement. The current system is doing exactly what you're saying, but it's not looking at correlations across. So if you look at this, the current system, given this movement, actually reports this. But the current system reports an A, reports a P, reports a Z, reports an E, reports everything. What we are saying is, you don't have to report them all. You do the compression on this string. That you send A, P, Z, E, then you don't send the next A, but you send A, P together as a smart encoding.
But you would have got more information had you sent, for example,
this. Yeah, which
could be, why not?
Yeah, in fact, so that's the interesting observation. So the current system is doing sending each of these, whereas lazy update is actually going at the cell level and doing a compression on that string. Now that string has much higher symbol generation rate, and this is a much lower symbol. But if you do the compression, then even though this is higher symbol generation rate, the average traffic still drops over this.
And then it allows you to address the issue that you had earlier, where you average uniformly over all the cells, right? It's in fact the finesse it.
Right, exactly. So, and that was the contribution of lazy update.
One thing I noticed is it seems like all the temporal information or time information is lost.
No, very good. Okay, I can address. In the scheme that we gave, we just did a movement, I mean, simulation runs we did as a movement-based scheme. Now, in essence, this lazy update operates on a symbol sequence. How you generate that symbol sequence is a separate question. Here, every time I moved, you generated it. But you can have things like either I move or every 5 minutes you generate a new symbol. It could be the same symbol. And you could use that time information with appropriate quantization as an additional state in the symbol. So,
simply the amount of time you spend at each of the pages.
right.
It's like you're taking continuous time markup chain and converting to discrete time markup chain. So state distribution will be different.
Yes. So if you look at the original lazy update paper, that paper compared all the three things: time-based, movement-based, generation of this string, and then the compression on that. But in general, given that most mobiles exhibit a high degree of stationarity at times, the general consensus is that sort of movement-based updates outperform timer-based, well actually distance-based updates outperform movement and timer-based updates. So you could do those, and for certain statistics you could do better, but not for the usual category of mobile nodes.
Are there any more questions? Thanks for coming, and let's thank the speaker.
Thanks very much.